All right, the lesson here is on experimental errors, as I have it on the title. So experimental errors is divided into two main types, I guess. You have systematic error and you have random errors. Now, hey, what's the difference between the two? All right, let's take a look at systematic error in terms of what is that all about. Okay, systematic error, most of the time, okay, you're talking about some sort of faulty experimental apparatus. Now, what does that mean? Faulty experimental apparatus. Well, a beaker. Okay, no, not really necessarily beaker, because you don't really measure with a beaker. If you are measuring a beaker, you should not measure with a beaker because they're very off. When you want to measure volume of something, you should use a graduated cylinder. But what if this graduated cylinder is chipped on the inside? Well, the accuracy of this graduated cylinder is going to be off, isn't it? So that's what we meant by faulty experimental apparatus. Okay, what if the balance that you're using, a digital balance that you're using, is non-calibrated? Well, again, you're not going to get the accurate results. Okay, you try to weigh something, if it's supposed to weigh 10 grams, it's going to give you 11 all the time. That's not a good thing, but that is what we call a systematic error. Now, it's not always just the apparatus to blame, but then sometimes it could be the design of the experimental procedure. Okay, your procedure just tells you to use too much or too little, which will give you an inaccurate result. Okay, so you should say, of course, that your results, like I spelled it wrong here, your results will always be, okay, I have trouble spelling words today. Okay, will always be off. Okay, so I guess we can do a little cheap example. Okay, you're doing trials, okay, of measuring something, and here's mass over here. The thing was supposed to weigh 10 grams, but for each trial, let's say you do 4 trials, you're not going to get 10 grams. You're going to get like 11, okay? You keep getting something, you keep trying, and you keep trying, and you keep trying, but you never, ever hit the right mass. You keep being off by 1. Well, that obviously has nothing to do with you. It's probably the measuring device that you're using, and that measuring device, as I said, is faulty. Hence, you are precise. Definitely, you are great in terms of precision, but you're not going to be accurate. All right, let's erase this. I'm pretty sure you know what I mean. Okay. Now, in terms of systematic error, there's actually 3 types of systematic errors that that we can differentiate. Okay. The first type, let's call A, is known as instrumental error, instrumentation error. So that's the faulty apparatus that I'm talking about. Okay. So as an example, leaky flashes. We have lots of those in our classrooms. Bad test tubes, leaky test tubes, they'll cause your results to be off. Okay? Another type of systematic error is known as experimental methodology error. Okay? So it has something to do with the method of your experimentation. So as an example, there's a couple of examples I can tell you, okay? If your balance that you're using to weigh something is non-calibrated, okay? Okay, you're not calibrating the apparatus. Sometimes things need to be calibrated. Or you're reading from, let's say, in a test tube, or a graduated cylinder, or a burette, which you'll be using soon. You're reading from, let's say, top of the meniscus. Okay, in case you don't know what a meniscus is, let's say this is your graduated cylinder. Okay, it has scaling here, and you fill it up with some sort of liquid that has some sort of cohesiveness in it, like water. You're not going to get this. Okay, you're not going to get this. Instead, you may see something like this. That is called a meniscus. Okay, that is a meniscus. Now, how do you read volumes when it forms a meniscus? Well, you always read from the bottom of the meniscus. Okay, so this is the right way of reading volumes, not the top of the meniscus. That will not be accurate. So if you're reading from the top of the meniscus, like what you're doing right there, that's an experimental methodology error. Okay, you always read from the bottom of the meniscus. Okay, you always read it here. Okay, whatever that is. All right, let's clear this up. Okay, there's actually one more example of an experimental methodology error. Okay, let's put that right there. Okay, is evaporation of chemical. Okay, you leave that up for too long. Well, if you leave things up for too long, things get evaporated to the air. Like, for example, if you have a certain concentration of acid, a very precise concentration of acid, and you let it sit out there without capping it, well, some of the water will eventually evaporate. That's nature. That's the way it goes. Well, because of that, the acid is now more concentrated than before. So you lost a bit of accuracy there. Okay. Due to temperature change. So make sure you write this down. Okay, so those are the two types. Okay, there's one more type which I will write down very soon. Okay, so the third type of systematic error is dealing with some sort of personal error. Okay, personal error as in like, hey, what color is this? And if you say pink, well, that's a wrong observed color because this is red. I hope you do see red, or else I want to get your eyes checked out. Okay, so an example is wrong observed color. Okay, so these are what we call systematic error. So what about random errors? What are random errors? Okay, because that's the second type of errors that is part of the experimental error. So random errors are due to things that is uncontrollable. You can't control it. Uncontrolled variable. Okay? Because it's uncontrolled, it definitely cannot be eliminated. Okay? But what you can do is you can reduce this error by doing it more. So reduce by trials. Okay? Which means at times you are going to be accurate, but you're not going to be accurate all the time. Okay? So an example here is I guess not being able to read an instrument due to fluctuations in readings. Now you're going to see that all the time. Okay? You put something very fine, like a powder, to weigh. But then as you weigh it, when you put that into the weigh dish and you watch the meter goes up, up, and then down, down, up, down, down. It's like it doesn't stop moving. So you're getting frustrated and you're running out of time. So you're just gonna pick whatever number that kind of situate the longest. Well, how do you know that is the right mass, right? You don't. So that's what we meant by fluctuations in reading, and you're going to see that a lot. You are. Okay, why does it fluctuate like that? Well, that's because of changes in the environment, like temperature. That changes, that's never that constant. The airflow of your lab, okay, sometimes a gush of wind come by, or maybe the air pressure wherever you're at. Okay? If that were to fluctuate, trust me, whatever you're measuring is going to be off. That's just the way it is. So that's what we meant by random errors. Okay? If the situation is perfect, hey, that's great. Your result is going to be accurate. But is it always going to be perfect? Because for every experiment that you do, you don't do it once. No, you don't do it once. You do it more than twice, I would assume. So are you going to hit the accuracy, the target, all the time? If you do, that's great. But you don't always. So that's what we meant by random errors. Okay? So just in case, if the pressure was fluctuating, the temperature is fluctuating, there's a gush of wind coming from all over the place all the time, you're not going to get the right results. So your best bet is to do more trials, and then you average them for, I guess, best practices. So those are the two types of experimental errors that I want you to know. So you have systematic error, okay, and random errors. All right, let's clear this page. Let me show you one more thing, and then that's it, okay? And we're going to continue with this next day, and this is called absolute and relative uncertainty. Okay? Absolute and relative uncertainty. What do you mean by uncertainty? Well, when you're doing an experiment and you're using some sort of instrument, like we said last time with significant digits, there's a certain uncertainty in terms of every measurement that you make. Whatever you think the volume is not always dead on. So let's say the bottom of a meniscus is 3 milliliters. Is it 3.00000 milliliter? Are you that accurate? No, you're not. So let's draw a graduated cylinder here. Let me show you. Okay, so you have, I guess, let's just make up something. This is obviously in the middle of something. So there's 10 milliliter, and there's your meniscus right here. So remember, you always read from the bottom of the meniscus, never the top. So if this is what you're looking at, okay, and you would say, okay, from looking at the bottom of the meniscus right there, okay, it looks like the volume here is 12 milliliter. Okay, now, can you be certain that this is 12.0 milliliter? Can you be certain that this is 12.0000 milliliter? You're not certain. Okay, nobody can be certain. So that's what we meant by uncertainty. Okay, now, for an apparatus that has an incrementation of 1 milliliter, 1 milliliter, 1 milliliter, 1 milliliter, okay, the uncertainty will be half of that. So let's write that down. So for this apparatus, the uncertainty is 0.5 milliliter. Why we chose 0.5? Okay, because that's half of a single, what we call increments. Okay, the incrementation of this apparatus is going up by 1 milliliter. So if you take half of that, that will be 0.5. If you know what I mean. Okay, so let's just say, let's maybe just clear this up a little bit. Let me change it to something else. Let's say the incrementation here is going up by 2. Okay, let's say this is 20, this is 24, this is 26. Okay, if you can see so 22, 26, 28, sorry. Okay, so as you can see, the incrementation here is going up by 2. Okay, so the uncertainty in this case will be 1 milliliter. Okay, I hope you know what I mean, but if you don't, make sure you ask me. Okay, always there for questions at all time. So let's write whatever I had back. Okay, you got 10, 15. Okay, let's go back here. So what does this half mean? Okay, what does this 0.5 mean? So we know for a fact that this volume right here is 12 milliliter, but as I said, you're not sure if this is dead on 12. So what we do here, of course, is that we would make up an uncertainty value. This number is not going to be just 12. This is 12.0 plus or minus, and what the uncertainty is that you determine. So that's 0.5, half of one incrementation. So if somebody would ask you, hey, what is the volume of this? You wouldn't say 12. You would say 12 plus or minus 0.5. Okay? That gives you sort of like a range, because this is actually representing a range. A range from 12 minus 0.5 to 12 plus 0.5. Okay? So this means 11.5 milliliter to 12.5 milliliter. Okay, so it gives reader a whole lot of leeway in terms of figuring out what this volume is. Okay, it lies anywhere between 11.5 to 12.5. That is what we call uncertainty. There's a little fancy word for that. That this is called absolute uncertainty. All right. Now, I'm going to show you a couple of mathematical operation now when you're being asked to add or subtract uncertainties. Okay, and then the next day we'll look at how multiplying and dividing uncertainty are done. So let's finish this off by looking at some mathematical operation. So let's take a look at here for addition and subtraction. Okay, what do we do with uncertainty? Well, very simple. You always add the uncertainties. Okay, so let's do a couple of questions here. One addition and one subtraction. So I have right here 15.5 plus or minus 0.2 centimeter plus 17.1 plus or minus 0.1 centimeter. Okay, what would the answer be? How would you report the answer? Well, you would do the addition of the true measurements as is. Okay, that will be 32.6. Okay, plus or minus. So now what do you do with these uncertainties? Well, as I said right here, you're going to add these uncertainties. So the uncertainty will just be greater, which is 0.3. Okay, that's how you would add two numbers with uncertainties in it. Let's do another example. Okay, I guess 26.4 plus or minus 0.1. Okay, you're going to subtract that by 10.2 plus or minus 0.3. Okay, this is a subtraction. So you would do your subtraction as you would do subtraction, right? So the answer would be 16.2. Now, plus or minus what? Do not subtract uncertainties, okay? Just like what the rule said, you always add the uncertainties. I made up this question in a way that it forms a negative answer, so it makes you think about, okay, what should I do? So don't forget, uncertainties for an addition and subtraction problem is always the sum. So that's how you would add and subtract uncertainties. So tomorrow, okay, we will look at how to multiply and divide two data or two numbers with uncertainties in it. And trust me, it's a little bit more work. All right, let's call it for the day. Bye.